Good morning, friends. Mrs. McBride here. I want to start today by telling you a quick joke. Why can't you tell a joke to an egg? It might crack up. All right. The game plan for yesterday was that you were supposed to watch a quick Edpuzzle video on the introduction to electricity. So today I want to give you some actual notes. We're going to be learning about 3 different things today. Those things are current, voltage, and resistance. And then next week we'll start getting more into how are those related and why are those important. Okay? So again, here I am in the note packet and it looks like I'm on page 8. All right, so the first thing we're talking about now is electricity. So we spent a bunch of time talking about static electricity, which was stationary charge. Now we're moving into what's called current electricity. And current electricity is, just by definition, moving electrons. Okay, so when electrons flow, that's called current. Okay. And specifically, if we were to define current, we would say this was the rate at which electric charges pass through a given area. Electric charges pass through a given area. And specifically, what types of charges are moving? Well, we know that electrons are the ones that are moving. So this is really the rate at which electrons pass through a given area. Think about it like you're looking at a river, right? So you look at the river and you think, wow, the river is moving really fast. Okay, the water is passing through a given area really quickly. Hey, the current of the river is high. Okay, or let's say you're looking at a little slow-moving stream. You think to yourself, wow, the current is really small, or that the rate at which the water is passing this given area is really small. Okay, so the way current works is the exact same thing. This is just, instead of moving water, it's moving electrons. Okay, what do you think would be a good symbol for current? You're right, capital I. Just kidding, I have no idea why that makes any sense, but the symbol is capital I. And the units are amps, which we're going to abbreviate as A. Now the way that I like to remember this is that these are both vowels. That's the only time that ever happens where I and A go together. And this is named after a French physicist named Ampere. And Ampere was a really smart kid. His name was André Marie Ampere. He had some bad things happen to him. His beloved first wife died. His father was guillotined. But he had some really awesome things happen to him, that he was the first one to connect electricity and magnetism into, dun dun dun, electromagnetism. And he was also the first one to come up with the idea that the periodic table should be grouped in a table form. But he was like, meh, I'm kind of busy, so I'm not going to worry about that. And then Mendeleev swooped in and, as you know, came up with the periodic table. All right, so current, it turns out, since current has units of amps, is measured by an ammeter. Why isn't it an amp meter? Well, that's a great question, which I don't know the answer to. It seems like it would make sense if it was an amp meter, but for whatever reason they call it an ammeter. Okay, and good news, we get an equation here for current, which says that current is equal to the change in charge over the change in time. And this just goes back to the idea that the rate at which charges pass through a given area is called current. Okay, so let me find my green sheet, which, as you know, is not green. Okay, and on here I just want to add this equation, which just says that current is equal to the change in charge over the change in time. And I'm down here going to write that I is equal to current in amps. All right? All right. Here's a quick sample problem. This one says, how many electrons per minute flow past a point in a circuit if it bears 11.4 milliamps of direct current? Now I've got some tricky things in there. Let's see if you caught any of them. There's two sort of problems that I've given you so far. Hopefully the first one you noticed was I gave to you by minute, and you know that we never do anything in terms of minutes, that we're totally going to want to use that in terms of seconds. The other one was this is in milliamps. It turns out that 1 amp of current is a really lot. If I took 1 amp of current and I ran it through your body, it would kill you. So a lot of times we talk about current in terms of milliamps. And remember, milli is just equal to e to the negative 3. All right, so if we use our equation, I equals delta Q over delta T, okay, the current that we have is this 11.4 milliamps. So this is e to the negative 3. And it wants to know how many electrons. Well, we got a problem here. How do we find the number of electrons? Well, we can use the charge. We can take and find the number of electrons by multiplying by the charge on 1 electron. So what we're really looking for is the number of electrons. Okay, and then we're dividing by the time, which in this case we said is 60 seconds. All right, so if we take our calculator, which I am not finding my calculator. Okay, sorry, here we go. And we're gonna multiply the two bottom numbers together and then divide by this. Okay, so take a second and do that. Or if you'd like to do it along with me, keep watching this video. Okay, so we're gonna take 11.4 e to the negative 3 times 60 seconds. Okay, and then we get this 0.684 number. We're going to divide this by 1.6 e to the negative 19. And what you get is a huge number. Okay, so this looks like it is 4.28 e to the 18. Okay, so if we do this and we say the number of electrons is equal to 4.28 e to the 18 electrons, I hope you're saying to yourself, holy guacamole, that is a lot of electrons. Again, this is only a milliamp of current. Imagine if we had a whole amp of current, that would be a lot of electrons. A quick note about current is that there's two different types of current, okay? And those two types of current are AC and DC. That was my best band logo drawing. Okay, AC is something called alternating current, and DC is something called direct current. Back in the day when they just came up with the idea of current, there were two people that were arguing over what type of current should we use. Okay, there was a gentleman by the name of Tesla, and this is Nikola Tesla, who actually has nothing to do with the cars right now, and a gentleman by the name of Thomas Edison. And Tesla, so Edison was the man, and he said, my way of coming up with current is the best. And Tesla's like, no, I am the best. But Edison had all this clout, and he was very famous. Tesla was just a poor immigrant. Well, if you want to know who won, the answer is Tesla. And the idea is that he came up with this alternating current that instead of current remaining flat, it's sort of, if we make a graph of current versus time, we would see that the current would alternate, okay? And an example of this is the type of current that comes out of your outlet. So when you plug something into an outlet, It's alternating current. Edison liked the idea of direct current, that if we were to make a graph of current versus time, that the current would stay the same. Okay? We see direct current in things like batteries. Okay? Think about it. Once the battery is done, it's no longer providing current. Okay? Once the power goes out, it's no longer providing current. If you have time, I would highly recommend watching the epic rap battle between Edison and Tesla. You will not be sad that you did. I just can't give it to you because it is not approved by school. So do yourself a favor and watch the epic rap battle between Tesla and Edison, okay? So again, we have two different types of current, AC, DC, which is exactly where the band name came from. And AC is alternating, which is the type of current that comes out of your outlet. DC is direct, type of current that comes from a battery. All right, that's enough about current. So let's go ahead and switch directions to something called electric potential difference, okay, which is a really fancy word for voltage. Now, I'm sure you've heard of the word voltage before because all different types of batteries have different voltages, okay? Do you need like a AAA or a AA that have a voltage of 1.5 volts? Do you need one of those like big camping batteries that has a voltage of 6 volts? How about everybody's favorite 9-volt battery, okay? Again, what voltage is, it's something called electric potential difference, okay? And what this is the electric potential energy per charge at a specific location. Okay, and again, what do we commonly call electric potential difference? Well, we commonly call it voltage. Now, the key word here is this word difference, okay? Electric potential difference. All right, so if you ever think about, here's some bad drawings coming up here. This is a battery, okay? And in order for a battery to work, you need a wire on the top and a wire on the bottom, okay? And this is going to provide you 1.5 volts. It's the difference in here that causes current to flow. If you only place a wire on one side or the other side, there is no difference and therefore no voltage. Same thing. Have you ever tried to plug something in? So here's your plug, okay, and here's this, okay? You know what this part is called, the little nose? This is called the ground, right? Do you notice not all plugs have a ground? Only things that really require a lot of power, like think about if you plug in your charger, okay, it doesn't have a ground. If you plug in your toaster, it does have a ground. Okay, so these are things that could get hot or require a lot of power. Okay, so anyways, what is coming out of the wall, one of them is at 0 volts. The other one of these is at 120 volts. And when you plug your plug into here, okay, what happens is that it creates some sort of electric potential difference. Okay, or there is a difference between these two voltages which causes current to flow. If you only plugged something in with one plug or the other, okay, it wouldn't work, okay, because it needs this difference in order to work. Now, is this side always 0 and this side is always 120? No. Remember, going back to Tesla, it's alternating. So it's going really fast. This side's 0, this side's 120. Boop, 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 boop. Back and forth, really, really fast, okay? Has anybody ever stuck their finger or a knife into an electric socket? Well, what happens is that you are at some point at 120 volts and your feet are on the ground. So there is a voltage or current that flows from here through your body zzz, to the ground. I one time mistakenly electrocuted my lab partner Julia because I told her that the circuit that we were working on, or the plug we were working on, was off, but it wasn't. Sorry, Julia. She stuck the screwdriver into this, and all of her muscles tensed up, and she couldn't actually remove her arm from the socket. Yikes. Okay. And then I just like to always talk about birds, because you always see birds birds sitting on a power line. How come they're not getting electrocuted like Julia? Well, because there is no electric potential difference. So whatever the voltage is of this high voltage line, it's the same, right? So since there's no difference, okay, both of their feet or their body is all at the same voltage, no difference, they're okay. All right, you guys are doing good. We're almost there. The symbol for voltage, wonderfully, is V, okay? And the units are volts, and this is named after an Italian physicist named Alessandro Volta, okay? This is the first and only time where we could say things like the voltage is equal to 9 volts, where both the symbol and the units have the same letter. So just keep that in mind. It's easy to remember. Okay. All right, last thing for today is we're talking about something called resistance. Ooh, I almost just knocked over my camera. So sorry. Okay. Resistance is a property that determines how much current will flow. So if you think back to current as a river, sorry, let me get this a little bit nicer. Okay, so if you think about current as a river, resistance is like a dam in the river. Okay, if I increase the resistance, okay, I put a little dam in the river, what happens to the current? Well, it decreases. Okay, last thing, symbol is capital R, and the units are ohms. And this is the Greek letter omega. It kind of looks like a little horseshoe. Okay, and this is measured by an ohm meter and is named after the physicist George Simon Ohm. Okay, no equation, don't need it. But what I did want to just write down is that we talked a little bit about a water example. So we said current, if we're talking about water, is very similar to the current of a river. Voltage is like the waterfall. Okay, as the current falls down the waterfall, it gets faster, okay? That's what provides the energy of the water, okay? And resistance is like the dam, okay? All right, friends, I will see you at the start of next week for some more information on current, voltage, and resistance. Bye, guys.